Okay, so once again, good afternoon. Welcome to Materials Science and Engineering class. Okay, so as you know, the mechanical properties of a material affect how it behaves as it is loaded. The elastic modulus of the material affects how much it deflects under a load, and the strength of the material determines the stresses that it can withstand before it fails. The ductility of a material also plays a significant role in determining when a material will break as it is loaded beyond its elastic limit. Because every mechanical system is subjected to loads during operation, it is important to understand how the materials that make up those mechanical systems behave. Okay, so at the end of this lesson, you should be able to define stress and strain, or to differentiate them, and state the Hooke's law, define Poisson's ratio, and what can we see on the stress-strain diagram. And you should be able to define toughness and hardness. Okay, so let's start. So these are the important terminologies for the mechanical properties of materials. So you have stress, strain, the Young's modulus, and shear modulus. So let's watch this first video to understand more about the stress and strain.
Do you know what a beam is? There are many different meanings of this word. In physics, we use this word in two ways. In optics, we say a beam of light. It can be thought of as a sequence of photons traveling in a straight line. In mechanical engineering, a beam is a long piece made of some material. It can be a wooden beam, a steel beam, or a concrete beam. We are of course interested in this kind of beam. Let's draw a rough general sketch of a rectangular beam. Okay, say we apply a downward force F on the surface area of a beam. Here, the force is trying to compress the beam from the top. Due to this, the beam will experience some stress. It is just an uncomfortable state experienced by the object, which is the beam in this case. The atoms inside are little too close than they want to be. This results in interatomic and intermolecular forces, and if the applied force F is within the elastic limits of the material, these forces bring back the object to its initial state when the applied force is removed. Mathematically, stress is defined as force per unit cross-sectional area. So it is F over A, where A is this cross-sectional area. What if I increase the force from F Newton to say F plus 10 Newton on this area A? Intuitively, we know that if we push it with a greater force from above, then the beam will experience more stress. Mathematically, this new stress will be F plus 10 over A. The numerator increased and the denominator remained the same. It means that this ratio is greater than this one. So if we increase the force, the stress will also increase. Next, what will happen if I increase the surface area from A meter squared to say A plus 10 meters squared? Will the stress increase in this case too? The stress will decrease in this case because the denominator increases with the numerator remaining constant. Now, what is the SI unit of stress? Any guesses? Stress is force per unit area. The SI unit of force is Newton, denoted by N, and that of area is meter squared. So the SI unit of stress is Newton per meter squared. However, this unit is given a name and it's called Pascal, denoted by PA. Now we know the basics about stress. What is strain? In very simple language, one can define it as change in dimensions per unit of original dimensions. When any object is under stress, it will change one or more of its dimensions. The amount by which the object's dimensions will change will depend on the force applied and the materials the object is made up of. In our example, L is the length of the beam and it's experiencing some force. Hence, it will deform and its length will change by, say, delta L. Strain is defined as change in length per unit of the original length. Mathematically, it is delta L over L. So what does this ratio do? Well, the ratio compares the change in length that resulted due to force with the original length of the beam. Here, strain is calculated in terms of length of the object. But the length may not be the only quantity changing due to deformation. We can also find the strain in terms of area and volume. Let's take an example of a sponge ball of volume V. When it's compressed, its volume decreases. So the strain in terms of volume is delta V over V. Note that delta V is the change in volume and not the volume of the deformed sphere. Let's take another example where a thin rubber sheet is stretched equally from the opposite sides with a force F. And that will result in a change in the area. So the strain experienced by the rubber sheet is delta A over A. Delta A is the change in area of the sheet and A is the original area of the sheet. So in the next video, we will see the types of stress and strain. See you there.
Okay, so now you were able to learn about the stress and strain. So let's take a look at these illustrations. So as you can see, in this illustration, you're able to see different or types of forces. So you have the tensile force. So take a look at the direction of the forces. It's outward of that material. And you have the bending force, direction of the force, downward. And then you have here the compressive force. Direction of the force is inward. And lastly, you have the shear force with the direction of the force. You have here the angle theta. So direction of the force going to the right, and here the direction of the force going to the left. And letter B shows the elastic material, the stress strain illustration of the elastic material. So you have here the slope, which is represented by the big letter A. And letter C here shows the stress strain diagram of a non-linear material. So it says here that the slope changes with the level of stress and the value of slope, which is variable. Okay, so E or the epsilon represents the strain, and this sigma is for the stress. Okay, so these are in support to the video that we have watched, or in reference to the video that we have watched. These are illustrations of the tensile. Okay, the first one here is how a tensile load produces an elongation and positive linear strain. So here, as you can see, the dash, take a look at the direction of the force, it's outward. So what happens here, this dashed lines represent the shape before this material has deformed. Okay, ito yung solid line. So after deformation. Now, letter B represents the illustration how a compressive load produces contraction. So take a look at this dashed line. This is the original shape of the material, and when it is being compressed, now this solid line shows us the result of the compressive force. So take a look at the direction of the force, it's inward. And letter C here is the representation of the shear strain, represented by gamma. Take a look at the direction of the force. So going to the right and to the left here, horizontally. And you have the angle theta here due to strain. Now, letter D is the schematic representation or an illustration of a torsional deformation. So due to twisting. Okay, so this is produced by an applied torque. Any questions so far? So I think the video that we have just watched is a very clear representation or explanation of the stress and strain. Okay, so again, let's highlight these parameters for the mechanical properties of materials. So we have the stress or the engineering stress, okay, represented by sigma, which is equal to the applied force, okay, over the cross-sectional area. So the unit of force is, of course, Newton for the SI, and then for the area is in square meters. Okay, questions? None. Let's proceed to another parameter, which is strain or engineering strain. It's basically represented by this Greek letter, epsilon, means the change in length or delta L over the original length of the material. Okay, so engineering strain or epsilon, subsequently called just strain. This is actually a unitless parameter since it's a ratio of the change in length over the original length. Okay, so here we have a unidirectional force is applied to a specimen in the tensile test. So this tool is used to determine the tensile stress and strain. So you have here the movable crosshead and the direction of force outward. So this, you can see here the cross-section head. Movement can be performed using screws, okay, or a hydraulic mechanism. So as you can see here, you have a parameter that can be determined, the diameter of this material and the gauge length. So, and the direction of, for the screw, the movement of the screws. So counterclockwise and clockwise direction in either sides of this tool for determining the tensile stress. Okay, any questions so far? So here we have the tensile stress strain curves for different materials. So we have metal for thermoplastic material, elastomer, and lastly for ceramics, glasses, and concrete. Okay, so note that these are qualitative, okay, representation. Now let's go to the shear stress and shear strain. So let's watch this video.
What really happens when we cut a cake using a knife? In physics, we could say that the cake experiences stress. Usually when we cut a cake, we hold the knife straight and apply the force perpendicular to the surface area. So can you guess what type of stress this is? It is normal stress as the force is acting perpendicular to this area. But what about these cross-sectional areas of the cake? The area on top is not the only area that experiences stress. As we pierce the knife in, this cross-sectional area experiences stress too. It doesn't look too obvious, but it does experience stress. We can also see that the force is not perpendicular to this area. It acts parallel to it as we are pushing the knife straight down. If the force acts parallel to the surface, it exerts shear stress. This stress tries to push the two surfaces away from each other and hence results in plastic deformation. So this is the basic difference between normal stress and shear stress. Normal stress is where the force is acting perpendicular to the area of contact, while shear stress is the force that acts parallel to the area. Let's take another example which explains shear stress better. Here's a beam and assume that it's fixed at its base. If we apply normal force to this cross-sectional area, then we know that the stress experienced by the beam will be normal stress, which is simply given by F over A, where F is the applied force and A is this cross-sectional area. This will result in a normal strain in the beam, which is given by delta L over L, where delta L is the change in length and L is the original length. Now suppose that we apply a force in this direction, parallel to area A. Again, the beam will experience some stress, but this time it will be a shear stress. The equation or formula for shear stress is the same as that of normal stress. Stress is simply the applied force per unit area, whether it's acting perpendicular or parallel to the area. What about the deformation in the beam by shear force? Here the deformation will be something like this. The object is stretched to some extent. Note that the beam is fixed to the base, so this cross-sectional surface will remain where it is, whereas the cross-sections above it will all get displaced to the right by increasing amounts. Now look at the maximum displacement here. Let's call it delta x. We know that this length is L. It's perpendicular to this. Also notice that there's an angle formed here. We can call it theta. With this information in place, let us define what shear strain is. Shear strain is simply equal to tangent of theta. Yes, shear strain is simply the tangent of this angle. But what is tan theta? We know that it's the opposite side over the adjacent side. Here, the length of the opposite side of theta is delta x, and length of adjacent side is L. So it's equal to delta x over L. So that's how shear strain is defined. Length of the deformation at its maximum over this perpendicular length.
Okay, so that was about the shear stress and shear strain. So again, let's highlight these terms. Okay, so shear stress is computed as the ratio of the pure shear force applied parallel. Okay, remember? Parallel to the upper and lower faces, so each of which has an area or cross-sectional area represented by A sub 0. So again, so shear stress is equal to, or shear stress is represented by this Greek letter tau. Tau equals to the force, the parallel applied parallel to the material. Okay? So ano naman yung force, ano naman yung stress na kung saan may force applied perpendicular. So we call it normal stress. Okay, so now let's go to the shear strain. So the same illustration as what we have seen in the video. So to determine the shear strain, so we have, of course, the same representation, which is the epsilon. So as you can see here, take a look at the figure. So the direction of the force. And so you have here the angle represented by theta. So as you know, strain is defined as the change in length of the material over the original length of that material. So here we can determine this shear strain by taking the tangent of theta. Okay, and the tangent theta, as mentioned also in the video, tangent is equal to, or as you know, tangent is the opposite side over the adjacent side. So the opposite side here is the length of this, the change in length. Okay, so or change in L or delta L over the adjacent side, which is the original length. Okay, now let's go to this parameter, torsion. So torsion is basically a variation of a pure shear. Okay, wherein the structural member is twisted. So like in this figure here, twisted in this manner. Now, torsional forces produce a rotational motion about the longitudinal axis of one end of the member relative to the other. So this is torsion. Now let's take a look at this video. So this video will talk about Hooke's law. Okay, before we proceed to the video, do you have any questions? Okay, none. So I think the video and the explanation in that video is very clear. So let's watch this video.
What are elastic and plastic deformations? Well, deformation means the change in shape and or size of the body. And the force which deforms an object is called deforming force. Elastic deformation is the case of deformation where the body regains its original shape as soon as the deforming force is removed. But what really happens? In a state of deformation, there is a restoring force generated inside the body resisting the deformation. Yes, a restoring force. When the body is in equilibrium, this restoring force is equal in magnitude to the deforming force and acts in opposite direction. And as soon as we remove the deforming force, this restoring force comes into play and restores the body to its original shape. Plastic deformations, on the other hand, are the deformations that permanently change the shape of the body. The applied force here is simply too much for the body to bear, and that results in permanent deformation. Now, which objects show elastic deformation and which ones show plastic deformations? Generally, all the objects show both types of deformations. Yes, for instance, if we just keep extending the spring forever, there will be a certain limit beyond which the length won't increase further. And if we try to apply more force, the spring may loosen and end up breaking. So the spring shows elastic deformation up to some extent, beyond which it results in plastic deformation. Spring is like a common example. Generally, almost every object shows both elastic as well as plastic nature. The elastic limits depends on the deforming force applied on the object and the properties of the material they are made up of. And it is important for engineers to note the elastic limits of things such as metal beams and concrete. That is, the limit to which they can uphold the load without getting permanently deformed or cracked. Now we come to an extremely important topic, the Hooke's law. Robert Hooke, an English physicist, stated that the empirical law in 1660, which is today known by the name Hooke's law. What does empirical mean? It means the law was derived using observations. It states, for elastic deformation in a string, the deforming force is directly proportional to change in length. Consider a spring of length L, whose one end is fixed from the end. Suppose the stretching force F is applied on the other end. Now let the change in its length be delta L. The law states that the force F is directly proportional to delta L. Now what do we mean in mathematics when one quantity is directly proportional to the other? It means that one thing is some constant times the other. So we can write force F is K times delta L, where K is the proportionality constant. This is the mathematical form of Hooke's law. In some textbooks, you must have noticed the presence of negative sign on the right side of this equation. The negative sign comes due to the slightly different version of the Hooke's law being followed. We can also define Hooke's law as the restoring force is directly proportional to change in length, And this, of course, is valid for elastic deformation only. The force taken here is the restoring force and not deforming force. The negative sign only tells us that the restoring force is opposite to the direction in which the length is changing. Another thing is that this law is not only valid for elastic deformation in a spring, it's also valid for elastic deformation in any material. But there is an assumption that this law is valid when the forces and deformations are relatively small. Also, there is a modified version of Hooke's law. It says that in an elastic deformation, the stress experienced by a body is directly proportional to strain. Before understanding this modified version, we need to understand what stress and strain mean. And we will do that in the next video.
Okay, so actually, you have already learned stress strain. Okay, so for most metals, stress and strain are proportional to each other as described by Hooke's law, which you have just watched in the video. Okay, so E is the constant of proportionality, in which it is in gigapascal or in PSI or pounds per square inch. And E is called the modulus of elasticity or the Young's modulus. Okay, so Young's modulus or the modulus of elasticity is or may be thought of as stiffness or the material's resistance to elastic deformation. So the greater the modulus, the stiffer the material is. Okay, so now let's watch the video about the elastic and plastic deformation.
When we hear the word elasticity, the first picture that comes to our mind is something like this. But is this really what elastic means? We will find that out in this video. Let's take an example of a helical spring. When a force of compression or tension is applied, the helical spring gets deformed, that is, it changes in shape or size. This force is referred to as the deforming force. And the ability of an object to regain its original shape when the influence of this deforming force is removed is called elasticity. More examples of such objects include sponge balls and rubber bands. When compressed or stretched, they get deformed, but they soon return to their original shapes. This self-reversing deformity the object goes through when forces applied and removed is called elastic deformation. But is there a limit to the elasticity of an object? Do elastic objects remain elastic forever? Not really. For instance, if a great amount of force is applied to a spring, it simply won't be able to stretch further than a certain point. But if the force becomes excessive, the spring will get permanently deformed and may even break if we keep increasing the force. Hence, the spring does not remain elastic forever. This type of deformation, where the object is unable to attain, or if it only partially attains its original shape once the deforming force is removed, is called plastic deformation. Now let me ask you a question. Suppose we have a rubber string and a string made of steel, both of very tiny thicknesses. Both are identical to each other in terms of size and shape. If we stretch them from both the ends with equal and opposite forces, then which one will stretch the farthest, assuming the deformation is elastic in both the cases? Quite obviously, the rubber string will stretch the farthest. The steel string would barely stretch, but it is important to note that it would indeed stretch no matter how little. It doesn't stretch as far as the rubber string because steel applies more resistance to the deforming force than the rubber does. Moreover, as soon as the force is removed, the steel string regains its original shape and size quicker than the rubber string. It won't allow a deforming force to change its dimension as easily. So, which one would you say is more elastic? Steel or rubber? You would think that the obvious choice has to be rubber, but unfortunately, that's incorrect. There is a general misconception that a lot of us have about elasticity. We think that the more the object gets stretched or compressed, the more elastic it is. But elasticity is not the same as flexibility. In the language of physics, the term elastic has a very different meaning. In physics, we say a body is more elastic if it resists more to the deforming force and reverses back quicker to its original shape after the force is removed. And since steel resists more and reverses back to its original shape quicker, it's more elastic than rubber. We can mathematically define elasticity as the ratio of stress to strain. We'll teach you what stress and strain mean in the upcoming videos. But get ready to be hooked to our next video on Hooke's Law.
Well, actually, I've just watched the video about Hooke's Law. Okay, so this is a great video explaining about the elastic and plastic deformation. So elastic deformation, let's highlight again. So it's a deformation in which the stress and strain are directly proportional. So now, so take a look at this diagram here. So this is stress and strain illustration. So strain is in the horizontal axis and stress is in the vertical axis. So you have here the slope, which is the modulus of elasticity. So this in red line here. So this is the direction of the load, and this is you unload the material. Okay, so if the elastic deformation is non-linear, as in the case for the polymers and the concrete, the tangent to the line will be used. So you have here tangent, or in this figure here, the slope. So tangent modulus is taken as the slope of the stress strain curve at some specified level of stress. So this is the tangent modulus. Okay, now we have the secant modulus, which represents the slope of the secant drawn from the original. So this is the secant modulus here. Origin to some given point of the stress strain curve. Okay, so this sigma 1 is being used here. Okay, the secant modulus between the origin and the sigma 1. And for tangent modulus, considering, of course, sigma 2 is seen here. Now, go back to the shear modulus. It's defined as the slope of the shear stress and shear strain. And this can be determined. So shear modulus represented by tau equal to this formula, G, and multiplied to epsilon. Okay, so now we go to the Poisson's ratio for elastic properties of materials. So Poisson's ratio is defined as the ratio of lateral and axial or axial strains. So this is the symbol for the Poisson's ratio. So you have negative epsilon, the x-axis over epsilon z, a sub z, or you can also consider epsilon to the y-axis over epsilon sub z. Now the figure shows the change in the cylindrical tube. So take a look at this figure here and how the strains and Poisson's equation can be applied. Okay, so this is the Poisson's ratio. Now when the force F is applied, okay, this is the force F, the specimen will elongate. Okay, a look at the elongation. So in the z direction. So this is the z direction and this is the x direction. And at the same time experience a reduction in diameter. So from this, you take a look at the dashed line here. So this is the original shape of the material or the cylindrical tube, and the red or solid representation. So this, as you notice, the diameter actually changes, right? So considering the Poisson's ratio in the direction, in the x direction, so you have the change in the diameter over the original diameter, which is d sub 0. So you have the new diameter, which is d sub I minus d sub 0 over d sub 0, or the original diameter. Now considering the direction, the z direction, so you have the change in length over the original length, which is, okay, alam niyo naman yung delta, diba? So it's the change in length. So the length that the resulted length after, you apply the force. So L sub I minus the original length over the original length. So that's the Poisson's ratio, depending on the considered direction. So elongated and due to the reduction in the diameter. Okay, so let's highlight again plastic deformation. So for most metallic materials, okay, you know that elastic deformation persists only to strains about 0.005. So as the material is deformed beyond this point, the stress is no longer proportional to strain and permanent. So non-recoverable or plastic deformation occurs. So the transition from elastic to plastic is a gradual one for most metals. So some curvature results at the onset of plastic deformation, so which increases more rapidly with the rising stress. Okay, so this illustration here, this is a typical stress strain behavior for a metal showing elastic and plastic deformations. So strain and stress. Okay, the proportional limit P, this is P, and the yield strength as determined using a 0.002 strain offset method. So you can see here the 0.002, okay, offset. Now let's go to tensile properties. So yielding is the stress level at which plastic deformation begins. And proportional limit for metals that experience this gradual elastic or plastic transition, the point of yielding, as you have seen in the figure, may be determined as the initial departure from linearity, straight, diba, of the stress strain curve. So yielding and proportional limit. Now we have the yield strength, the stress corresponding to the intersection of this line and the stress strain curve as it bends over the plastic region. And on the other hand, tensile strength is the stress at which, or at the maximum on the engineering or stress strain curve. Okay, so this figure shows typical engineering stress strain behavior to fracture point F. Okay, so I think point F natin. So the tensile strength, or TS, here in the figure is indicated at point M. So this is point M. The circular insets, okay, you have here circular insets, represent the geometry of the deformed specimen at various points. So you have here this point, okay, along the curve. So these are the insets or circular insets. Okay, now we have the term ductility. So it is a measure of the degree of plastic deformation that has been sustained at fracture. So material that experiences very little or no plastic deformation upon fracture is termed brittle. Okay, now we have the schematic representations of tensile stress, strain, behavior for brittle and ductile materials loaded to fracture. So this, as you can see, we have a color-coded representation here. So this part or your stress strain diagram is where the material becomes ductile, and here for brittle. Okay. Now we have the term toughness. So toughness, it is a measure of the ability of a material to absorb energy up to fracture. Right, this is the area under the stress strain curve up to the point of fracture. So stress represented by sigma and strain is epsilon, unitless parameter. So for a material to be tough, it must display both the strength and ductility. So remember this, for a material to be tough, it must have both the strength and ductility. Now we have the term true stress. So what is true stress? So we know that the formula of stress is the applied force over the cross-sectional area. So true stress is defined as the load F divided by the instantaneous cross-sectional area over which deformation is occurring. So again, if you're given a problem or if you have a problem to solve, so stress is equal to the force over the cross-sectional area. And the unit of force is in Newton and area is in square meters if it's SI. Okay, or basically in Pascal. Now, true strain is defined as the natural logarithm of the final length, okay, final length represented by L sub I divided by the original length or L sub O. Okay, remember? So true strain is the natural logarithm of the final length over the original length. Okay, so these equations are the relationship of the engineering stress and the true stress and strain. Okay, this symbol here, or sigma sub E, is the engineering stress, and this is the true stress. So if you are asked to solve for the true stress, you can actually utilize the value of the engineering stress, okay, multiplied to 1 plus the strain, okay, or the epsilon. Now for the true strain, which is represented by epsilon sub t, equals the natural logarithm of 1 plus the engineering strain. Okay, so these equations will hold only on the onset of necking. Okay, so for some metals and alloys, the region of the true stress strain curve from the onset of plastic deformation to the point at which necking begins may be approximated by this equation. So true stress is equal to K times the true strain raised to N, or taking log both sides. So you have the log of this true strain equal to the log of the product of K times the true strain raised to N, can be represented by this equation. Okay, properties of the logarithmic functions. So in this expression, K and N are constants and will depend on the condition of the material. Okay, so again, one factor that we have to consider is the material, type of the material. So whether it has been plastically deformed or heat treated. The parameter N is often termed the strain hardening exponent. Okay, again, N is the strain hardening exponent and has a value less than unity, okay, or less than 1. So by plotting the log of stress strain curve, you will get the values for K and N. Now we have the last parameter here for the mechanical properties. We have the hardness, measure of the material's resistance to localized plastic deformation. Okay, example, a small dent or a scratch. Quantitative hardness techniques have been developed in which a small indenter is forced into the surface of a material to be tested. Now the depth or the size of the resulting indentation is measured, which in turn is related to a hardness number. The softer the material, the larger and deeper is the indentation, and the lower the hardness index number. Okay, so this is our topic. This actually summarizes our topic about the mechanical properties of the materials.